I'm Filippo Coletti. I'm assistant professor of aerospace engineering and mechanics at the University of Minnesota, and I'm a faculty member in the St. Anthony Falls laboratory. So my research has two main axes. One is the biomedical flow side, and one is the environmental flow side. I really study fluid flows in general, but the specific application I care about are respiratory and cardiovascular flow on the biomedical side, and transport of particles in turbulence on the environmental flow side. For the transport of particles in turbulence, it's very important for us to know, for example, how fast dust and powders, pollutants can settle by gravity in turbulence. But in practice, if you're thinking of a cloud of pollutants coming out of a chimney, for example, in a power plant, and you know that it's going to be transported with the wind, you want to know how fast that falls, so you know if the pollutant is going to fall on the ground a mile downstream or 100 miles downstream. To understand this problem of how fast particles settle, what we wanted to build was something that could reproduce the type of turbulence you have in a high altitude sky, but in our laboratory. And so to fix these problems, remove the effect of the walls and produce turbulence without a big mean flow, we built Claudia, a cloud of inertial aerosol. It's a facility that basically generates high intensity turbulence, but without having any mean wind inside. Right now we're actually looking at small flies, fruit flies specifically, and how they fly in turbulence. So we put them in a small cage that vibrates, and that kind of kicks the motion of the flies. And then as they fly in air, we look at their trajectories with and without an underlying turbulent flow. The idea is that by doing that, we might be able to understand how flies are able to navigate so well in a quickly changing turbulent flow, whereas we, let's say pilots of airplanes, we are in so much trouble trying to navigate within this random gaseous turbulence. My students tend to have either a mechanical engineering or an aerospace engineering background, although when they join my group, they naturally get to learn more interdisciplinary topics. So in general, they need to come in with a strong background in fluid dynamics and engineering science, but then they need to be open at learning completely different topics and areas. I think SAFOL really has the structure that it does have because of a strong group of young students. They gather together around an advisor, but then they also talk with each other across different groups, and they form a kind of strong collegial environment of young scientists. I think this is it's not maybe a unique feature, but it's a very distinctive feature of SAFOL, and they foster them in their growth such that some way, maybe halfway to the completion of their degree, they actually can come up with their own questions and even bounce ideas off each other and produce a fertile research environment which is goes a lot farther than what the role of the individual advisor is.